Howdy, welcome back everybody. This is the third video in the series on how to determine molecular geometry based on VSEPR theory. The learning objective for the whole series of videos, all three of them, is for you to be able to predict the three-dimensional geometry of any molecule, practically any molecule, using VSEPR theory. At the end of this video, you should be able to predict the three-dimensional geometry of molecules with 5 or more electrons around the central atom. Now let's keep in mind that when we say 5 or more, we're only going to talk about those with 5 and 6. Those are the ones that typically happen in normal chemistry. We don't see anything more than 6 electron domains. So here we have a molecule of arsenic pentafluoride. Arsenic pentafluoride has 5 electron domains, 5 bonding domains. 1, 2, 3, 4, 5. Now, this shape is awfully interesting. It's actually the most interesting, in my opinion, of all the shapes, of all the geometries, because it looks like this. We are trying to represent here a 3-dimensional molecule on a 2-dimensional space. So when we really are looking at it, we should draw it in 3 dimensions here, which we have tried as best we could. And notice that is represented up here on the molecule. And I can overlay these two, and look, it looks pretty good. And when you overlay them, and when you overlay them, you can see that we draw the bond that's going back here using these dashes, and the bond here that's coming forward with the wedge. That's called the dash wedge notation, and it's just convenient for us to keep in mind the geometry of the molecule. Now, one other thing is, because there's 5 things trying to be equally spaced around the central atom here, those 5 things, 1, 2, 3, 4, 5, take a special orientation. This orientation has these 3 atoms that are kind of around the belly of the molecule, the middle of the molecule, and then these 2 atoms here that I'm going to highlight in blue that are on the top and bottom. Okay, it may be easy to compare this to the Earth here. I'm going to draw the Earth, and if I'm really good, I may be able to draw like a little island or whatever. Okay, and so if we take a look at the atoms in the blue, they're on the top and the bottom. Well, the thing that goes through the top and the bottom of the Earth is the axis of the Earth, and so these are called axial atoms. Okay, axial atoms. Now, the line that goes through the middle of the Earth this way, I'll do it in black because that's what these are. This is called the equator. So these are equatorial atoms here, there, and there. And so that 3-dimensional shape is unique because the bond angle here between these black atoms is actually reminiscent of a trigonal planar molecule, because there's 3 things shoved around the belly of that, so it's going to be 120. But there are also this bond angle here to here, which is a right angle, so that is 90 degrees. So you have all sorts of things going on here, and it makes for kind of a really important or really interesting molecule. So if we look, that again overlays pretty well with that. So I'll get rid of that. But the shape of this now is called bipyramidal. Okay, now we can move down to something like sulfur tetrafluoride. And for those people who are paying very close attention, I will tell you that this is my favorite molecule. It has 5 electron domains and 4 bonding domains. So when we do that, we're actually going to start by getting rid of a equatorial atom. It's just the way it works. Okay, so it actually kind of looks like this. Notice we have gotten rid of an equatorial atom that would have been out here. Okay, now this shape is, and this is why it's my favorite, Okay, this shape is called Seesaw. And the bond angle, like anything with 5 electron domains, is going to be 120 degrees here and 90 degrees here, between that one, and between that one, between that one, and that one. I think you get the idea. Okay, but why is it called Seesaw? Well, it's very simple. And this is, again, why I like it. So if I take this and I rotate this guy, okay, and look like this, okay, and I put a person here, and I put a person here, okay, and then I can take this and I can go, look, I'm going up and down and up and down. It actually looks like a seesaw. So that's like why it's my favorite. Okay. You'll probably see something like that on a future skill assessment. Now we can come down here. We'll speed up a little bit, but this guy here has 3 bonding domains. It, of course, has 5 electron domains. And so now something funny happens with this one too, because when we do this, we lose another equatorial bond. And then when we lose the equatorial bond, we notice that now all we have left are these 2 90-degree angles. So that shape has a bond angle of 90 degrees, and let's see if you guys can figure out what the shape is going to be called when I rotate it this way. Let me get rid of this stuff. Okay, when I get this way, anybody want to take a guess out there? Okay, we're going to call that T-shaped. Yay! Okay, great. Now, if you have 5 and 2 or 5 and 1, these are both linear, and 5 and 2 has a 180-degree bond angle, and anything, again, with 1 bonding domain doesn't have an angle, no angle. Okay, so now what if we have 6 electron domains? So what if we have sulfur hexafluoride? Sulfur hexafluoride now has 6 electron domains and 6 bonding domains. And again, we're trying to represent a three-dimensional shape, three-dimensional molecule on a two-dimensional computer screen here. And sometimes that doesn't work. So let's bring down the three-dimensional model. And hey, look, if I overlay that, look, it kind of all just lines up pretty well. Okay, and if we're going to use dashes and wedges, these here should be dashed, indicating that they go back, and these guys should be wedges, indicating that they come out. So those guys are kind of the belly of the molecule, and these are the axis of the molecule, so they're actually equatorial and axial bonds. So this molecule, helps if I move and not draw, but this molecule is called octahedral. Octahedral, and you'll notice that the bond angle is going to be 90 degrees no matter what you do, 90 degrees, how you manipulate this, all the bond angles there are going to be 90 degrees. Now, why is it octahedral? This is, again, another interesting thing that happens. Okay, if we look here, octahedral, we have this shape that we can overlay. Now, this shape is an 8-sided solid figure. Hedron in geometry means solid shape or three-dimensional shape, and octa tells you how many faces there are. So there's one face here, one face here, one face around the corner, and back here you can see, and then another face there, and then 1, 2, 3, 4 faces here, for a total of 8 faces. So this guy, when you overlay, you're like, oh wait, the central atom can sit right in the middle, and notice that each exterior atom can sit at the vertice of the octahedron. So that's why that is called an octahedron, because if you were to make a three-dimensional object out of it, it would be an octahedron. Now, try to get rid of some of this stuff. So now let's go to the next one. What if we have bromine pentafluoride? That has 6 electron domains. 1, 2, 3, 4, 5, 6. And it has 5 bonding domains. Now, in this case, this shape looks like this. And now, these guys are equatorial, and then there's one sticking up. So guess what? This guy is a square It's called square pyramid. Or if you want to use the adjective form of that, it could be square pyramidal, whatever. I'd be happy if you just remembered that it was square pyramid something or other. Okay, what if we have something like this guy? This is the ICl4 minus ion. It may look familiar to you. This ion now looks like this. We've gotten rid of both axial atoms, and look, they I could overlay them, rotate this, and look, hey. And so what that is that is just a square plane. So guess what? So we have 6. Ooh, that's a funny kind of pen. Maybe I'll try the regular pen. We have 6 and 4. That's going to be square, S-Q-U-A-R-E, square planar. And as with anything with 6 electron domains, there's 90 degrees, or the bond angle. Okay, so if we move down to 6 and 3, and there's not very many examples of 6 and 3, but that looks like that. You'll notice that 6 and 3 looks a lot like 5 and 3 on purpose. So 6 and 3, that's going to be T-shaped, and the bond angle is 90. Anything that has 2 or 1 electron domains are going to be linear. So 6 and 2 and 6 and 1 are linear. And a linear with 2 electron domains has a 180 degree bond angle, and a linear with 1 electron domain has no bond angle. So let's try it yourself. Pause the video right now and see if you can come up with the electron domain geometry, or the geometry and the shape and the angle, whatever you want to say, of all of these molecules. So I assume you paused the video, so now we go over the answers. Okay, this is 5 electron domains. Electron, I'll put just an E here, and a B, electron domains, bonding domains. So that is bipyramidal. Okay, pyramidal, get the spell in Walsh, and the bond angle is 120 and 90 degrees. Here we have 6 and 4, so if we have 6 and 4, that's going to be square planar, and that's going to be 90 degrees. And this is my favorite guy again. Here's Si4. That's 5 and 4. And remember, when you have 5 electron domains and 4 bonding domains, that's going to be a seesaw. And anything with 5 electron domains will have a bond angle of 120 and 90. Okay.